Okay, let's start part 2 with number 22. Again, we're trying to factor these completely. So it says t to the fourth plus 16 u to the fourth. You probably noticed that all of these are perfect squares, right? T to the fourth is a perfect square, 16 is a perfect square, u to the fourth is a perfect square. So you think you might be able to use the difference of two squares, but there is a problem in that this is plus, okay? And there is no process we have for a sum of two perfect squares, or perfect fourth powers, which is what these are, right? So this one is actually going to be irreducible. Now, if there was no u here, we could actually set it equal to 0 and try to solve it by taking fourth roots, and we're going to get imaginary numbers, but because of the u, it doesn't work. So this one's just going to be completely irreducible, which means that it's factored already. That's as far as we can get. Alright, let's move on to number 23 then. X squared plus 18x plus 9. We're going to try to factor it completely. I see a trinomial, and when I see a trinomial that is a quadratic, that's a square, right? We are going to try to factor by x factor. So if a times c is 1 times 9, that's 9. B is 18. Two numbers that multiply to make 9 and add up to make 18, that's impossible, right? You guys should be able to see that that's not going to happen. Alright, they still want us to factor even in finding imaginary or complex roots. So that means that I'm going to go ahead and try to solve this using the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, a is 1, b is 18, c is 9. So we're going to use those three values and plug them in. So it's going to be x equals negative b, that's 18, plus or minus the square root of b squared, 324, b squared, right, minus 4 times a, which is 1, times c, which is 9. There you go. All over 2 times a, which is 2 times 1, which is just 2. Alright, let's keep simplifying that. Negative 18 plus or minus the square root of 324 minus 4 times 9, that's 36, right? So 324 minus 36, that is 288. Okay, all over 2. Alright, and now we're not going to leave this like this because it's completely not simplified. I am actually going to go through the process of breaking down that radical. Something that you guys did back in Integrated 2. We didn't actually practice it that much in class. So what I'm going to do is I'm going to break down the 288 into... what goes into it? Well, for sure 2 because it's an even number, right? So 2 and 144. Done with that. 144 is 12 and 12. I know that's a perfect square. You could actually stop there already because you see that there's a 12 and another 12, so you could actually stop there, but I don't think you guys are used to that, so let me go ahead and continue. This is 3 and 4, so the 3 is done, and this is 2 and 2, and now that's done. This is 3 and 4 again, the 3 is done, and this is 2 and 2 again, and now those are done. So what you have is the square root of, looks like 1, 2, 3, 4, 5 2's. So 2 times 2 times 2 times 2 times 2. And 2 3's. Right? 1, 2. 3 times 3. There you go. And now remember the process was to look for pairs and break them out. Here's a pair of 2's. One of them comes out. I'm going to write it over here. The other one dies. So they're both gone. Here's another pair of 2's. One of them comes out. I'm going to write it here next to the other 2 that came out, and the other one dies. That single 2 stays in there. It has no partner. But the 3's, there's a pair of 3's. We're going to take them out. Pair of 3's. One of them comes out. The other one dies. What's left inside is that single 2. Just the 2. Like that. And the numbers that came out, 2 and 2 and 3, that is 12. They all stay outside. So x equals negative 18 plus or minus 12 radical 2 all over 2. And now to finish simplifying that, what you need to do is look at the numbers that are outside, nothing inside the radical. That does not simplify. But the stuff outside, 18, 12, and 2, and notice that they all have something in common that you can divide them by, which is 2. So divide them all by 2, and you have x equals negative 9 plus or minus 6 radical 2 all over 1. Now since it's all over 1, I can actually just drop the 1 and it's just negative 9 plus or minus 6 radical 2. That means that there are two solutions here. X equals negative 9 plus 6 radical 2 and x equals negative 9 minus 6 radical 2, right? The conjugates, those two are the conjugates that come out of it. And so now I can write the final factored form, because remember, that's what it's asking me for. Using these two roots, what does the factored form look like? It looks like this. X minus, right? It's always x minus, and then all you got to do is plug in those roots that we just came up with, those zeros that we just came up with right there, and we'll be done. So when I put in negative 9 plus 6 radical 2 right here, since it's x minus, this minus with this negative 9 will turn it into plus 9 minus 6 radical 2, right? Basically, the negative 9 becomes positive 9, and the positive 6 radical 2 becomes negative 6 radical 2. Same thing for that one. The negative 9 turns into positive 9, and the 6 radical 2 is plus 6 radical 2. That is the factored form of the trinomial that we started with. This trinomial does not have rational solutions. All of its solutions, both of its solutions are irrational, right? Negative 9 plus 6 radical 2, negative 9 minus 6 radical 2. So if we write it in factored form, that's what it looks like. Alright, let's continue with 24. N to the 6 plus 125. This one's not as obvious. It's kind of tricky. You should see that 125 is 5 cubed. Right? That is one thing that you should see. And that helps you because that means that maybe I'm looking for perfect cubes. Now this one's the one that's a little tricky to see. This is a perfect cube. I know that it is a perfect cube because this 6 is a multiple of 3. So for example, this is a perfect cube. Right? We know that. That's easy. But this is also a perfect cube. And this is a perfect cube. And this is a perfect cube. And this is a perfect cube. All of these are perfect cubes because the powers are multiples of 3. This is a perfect cube because it's x cubed. That one's easy. But the next one, x to the 6, that's a perfect cube because it is x squared cubed. Right? Because the rule for these types of problems is to multiply the power, so that's x to the 6. And so it ends up that it is a perfect cube, right? If there's a power of 3, it's a perfect cube. The next one is x cubed cubed. Cubed. And the next one is x to the 4th cubed. And the next one is x to the 5th cubed, right? All of those are perfect cubes because they are multiples of 3. So we can do that with this one over here. And n to the 6 is the same thing as n squared cubed. N squared cubed plus 5 cubed is what I have. And now I can use my rule for perfect cubes, which is going to be n squared plus 5. And then, let me erase all this stuff over here so I can continue. Remember the rule for perfect cubes? All I did right now is just take off the powers of 3, right? So it's n squared plus 5. And then for this one, remember, square the first one, that goes here, times each other, but change the sign, that's in the middle. Square the last one, that goes there. So let's do that. Square the first one, that means n squared squared, that's n to the 4th. Times each other, but change the sign, so that's 5n squared, but negative 5n squared. Square the last one, that's 25. Alright, so on this one, we're done. Right? There's nothing else to do there. There is no process for me to factor this. I can't use x factor. I can't use the quadratic formula because it is not a quadratic. But for this one, I can keep going. N squared plus 5, what I'm going to do with it I set it equal to 0. Subtract the 5. And I get n squared equals negative 5, right? And then take the square root of both sides. So I can solve that one. Now you might say no because it's negative, but now we know that we can actually solve it even if it has a negative inside, because that's just I. That's I radical 5. And remember, when you take the square root of something, you have to include the positive possibility and the negative. So it's plus or minus I radical 5. I'm going to split those up into positive I radical 5 and negative I radical 5, right? Two separate ones. And so from those two, I can come up with two factors. Always x minus I radical 5, x plus I radical 5, and then the other final factor is the one we couldn't factor, this one. We can't do anything with that one, so we leave it alone. N to the fourth minus 5n squared plus 25. And now it's completely factored. There are two zeros that we found, and there are four others that come from here that we have no way of finding right now. Alright, let's move on to number 25. I'm really hoping that we can do this one by factoring by grouping, because if not, we're going to have to find all the factors of 567 and test them out using synthetic division. So let's see. First I'm going to erase this to get it out of the way. I'm going to try to set these two together and then these two together and see what I can break out. For the first pair, I see that they both have x squared, and that's it. So factor out x squared. Divide by x squared on both of those. That leaves me with x squared and then x plus 7. For the other pair, I'm going to do the division here on my calculator. I really hope that I can divide by negative 81, because if I can't, that means synthetic division. That's what it means. So let me see, 567 divided by 81. Yes, it's 7. So that means we factor out negative 81, and we're going to get x plus 7. Perfect. Awesome. That means that synthetic division works here. So x plus 7 is my factor, one of my factors, and the other one is x squared minus 81. And that works awesome, because look at x squared minus 81. That's a perfect square minus a perfect square, so I can keep going. That's x plus 7, and then x plus 9, x minus 9, right? One positive, one negative. Done. You factored it completely. There's nothing else to do there. The solutions, if they were looking for the roots, would be negative 7, positive 9, and negative 9, right? But they're just asking us to factor, so that's it. Alright, let's move on to 26. This one looks a little bit tricky, but don't forget that my first step that I always tell you guys is to factor out the GCF. And so I do notice that they all have something in common, right? It looks like they're all divisible by 3, right? So we're going to factor out 3. And also, they all have z. So factor out 3z. When you factor out 3z, on the first one, you're going to have 9x squared. The middle one is just going to be 12x. And the last one is just going to be 4, right? 12 divided by 3 is 4, and the z's cancel. And then what I'm going to try to do is use x factor on this one, because it's a quadratic, right? A quadratic trinomial. So let's try x factor there. I got 9 times 4, which is 36. 12. Look at that. Works perfectly. 6 times 6, right? Alright, so I'm going to keep going. Leave the 3z alone. You can also just forget it for a while, but make sure you remember to write it there at the end. I'm going to leave it there. Now, this 9x squared plus 12x plus 4 becomes, because of these 6's, becomes 9x squared plus 6x plus 6x plus 4. And now we're going to factor by grouping in there, right? We're going to group these two together. We're going to group these two together to see if I can factor something out. And you can. For the first pair, you can factor out 3x. 3x and 3x. For the second pair, you can factor out 2. Right? That's the only thing they have in common. So here's what we have. We have a 3z outside. Right? And then inside this big parentheses, which I'm going to turn to brackets so that I don't get confused, you have 3x. And what's left when we factor out the 3x from the first pair? We have 3x, right? Because it's 9 divided by 3, x squared divided by x. So 3x. 6 divided by 3 is 2, so plus 2. Now for the second pair over here, 6 divided by 2, that's 3. So we have a 2 outside that we factor out, and then 3x. 4 divided by 2 is 2. There you go. That's what we have. And now I see that it's 3x plus 2 and 3x plus 2. So what I have is 3x plus 2 and 3x plus 2. And let's not forget this 3z that's in front. And that is your final answer. 27 is pretty simple. I'm only doing it just to show you guys that it's pretty much impossible to solve. X cubed plus 65. That's a perfect cube. That is not. So this one's irreducible. Irreducible. There is a way to find the zeros, which is to the roots to which is to set it equal to 0. It would look like this. And then you would subtract 65. And you would get x cubed equals negative 65. And then you would take the cube root of both sides. And so x would equal whatever the cube root of 65 is, of negative 65 is, which is some decimal number, okay? Which cannot be simplified. I don't think 65 is, let me just double check that. If I factor 65, it's 5 times 13. No, there's nothing to simplify there. So no, it cannot be simplified. It's going to be just some decimal. So basically it's the cube root. By the way, I did forget to put that. It should be cube root, not square root. Because if you want to cancel a cube, you need to take the cube root. So it'll be the cube root of negative 65. Like that. That would be your x value, and it would have a multiplicity of 3 because it happens 3 times because of this x cubed, right? So they're all the same thing. But anyway, we're not going to worry about that one. I was just showing you that you can actually find solutions, but you can't factor it. It's irreducible. Alright, 28. This was just a reasoning problem. All you got to do is read it and answer what you think. It says, consider the polynomial function 6x cubed plus 7x squared minus radical 6x minus 2. Is it possible to use the rational root theorem and synthetic division to factor this polynomial? Explain your reasoning. First of all, the rational root theorem is the one that tells us that we can factor all polynomials that have rational coefficients by looking at the constant term at the end, finding their factors, and looking at the leading coefficient and finding its factors, and then making up fractions, right, m over n out of that. And those are all the possible rational factors of it. However, we cannot use it here simply because of this. Right? You guys look at that one right there. The coefficient of that x is radical 6, negative radical 6. That's not rational. So that means that we cannot use the rational root theorem or the rational zero theorem, which is the same thing. Right? So basically your answer is no. The negative radical 6 is not rational. All of the coefficients should be rational. And what does rational mean? Numbers like 1, 2, 3, 4, 1/2, 1/3, 4/7, negative 2 over 6. All of those are rationals. Negative 5 over 9. I don't know, I'm just making up numbers. All of those are rationals. Which ones are not rational? Radical 6, radical 3, radical 2, pi. Radical 2 over 5, right? As soon as you have a radical in there, it's not going to be rational. The cube root of 15, pi squared, right? Anything that has any number that cannot be expressed easily as a simple fraction, where the first number is a whole number and the second number is a whole number, the numerator is a whole number, the denominator is a whole number, it's not rational. All of these are not rational. So if you see any coefficients that look like that, then you can't use the rational root theorem. You can't use synthetic division. It doesn't work. Alright, so same question, 29. Consider this polynomial function. Now it should be obvious after I explain 28 that no, you cannot use synthetic division in the rational root theorem because of this term right here, right? So we're going to answer no, pi is not rational. They have to have rational coefficients for you to be able to use the rational root theorem and synthetic division. Number 30, what does the rational root theorem find? And this is just a question just to show you guys that sometimes people say that the rational root theorem is going to tell you what the solutions are, what the roots are, what the zeros are. And that's not true. So for example, let me just give you a quick example. Let's say I have a polynomial. P of x equals, I'm just going to make something up, x cubed plus 3x squared plus 15x minus 20. Don't know, just make that up. Probably doesn't even have any roots that we can find using the rational root theorem. But let's say I have that. The rational root theorem tells me that I can take the constant over here, 20, find all of its possible factors, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20, right? Find all of its possible factors, take the leading coefficient, which is 1, and find all of its possible factors, which are just 1. And then I can make fractions out of this. Remember, 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, 20 over 1, and so on. If there was another number here, then I would have to use 1 over whatever that number is, 2 over whatever that number is, and so on. Right? I would have to find all of them. And then what the rational root theorem tells me is that if there is a rational root to this polynomial, if 1 exists, it's got to be one of these. Otherwise, it doesn't exist. Otherwise, all of the roots are either imaginary or irrational, right? So if there is one that is rational, it must be one of these. It has to be one of these. It doesn't tell me what it is, right? I don't know which one it is, but it does break it down for me so that I know where my solutions could possibly be. It's gotta be one of these if it does exist. It doesn't tell me which one it actually is. I don't know if it's 1 or 2. I have to test it out, but it tells me which ones to test out. Which ones are the possible rational roots of a polynomial function. Okay, 31. Describe the process for finding the rational zeros of a polynomial function with integer coefficients. So there's a few steps you have to take in order to find the rational zeros or rational roots of a polynomial function with integer coefficients. So like the one that I just made up in the last problem. Let's make up another one. P of x equals x cubed plus 4x squared minus 7x plus 15. I don't know, just making something up. What is the process that you would use if I told you find the roots, find the zeros, the rational zeros of this? What you would do is you would take the, you know what, to make it a little more interesting, let's put a 2 here. There you go. That way we can follow the process and follow all the steps. You would take the 15 and find all of its factors. Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Right? And then you would take the 2, the leading coefficient, and find all of its factors. Plus or minus 1, plus or minus 2. And then you would find which ones you need to test. What are the possible zeros? They're made up of these divided by these, right? All the fractions that you could make from these divided by these. So what would you test? You would test out all of these. Testing values. Possible testing values are 1 over 1. I'm going to leave off the plus or minus, but assume that all of them have a plus or minus in front of them, okay? 3 over 1, 5 over 1, 15 over 1. That would be this one over this one, this one over this one, this one over this one, this one over this one. Now you got to do the same thing, but now over 2. So the next ones would be 1 over 2, 3 over 2, 5 over 2, 15 over 2. And so if there is a rational root for this polynomial function, that doesn't mean that there is one for sure. We don't know if there actually is a rational root. It might not have any rational zeros. But if there is one, it's got to be one of these. Of course, plus or minus, right? If one exists, it has to be one of these. And so what would be the next step would be to test them out using synthetic division, right? And we would test it until we found one that worked. If none of them work, then that means that it doesn't have any rational zeros. That means that all of its zeros, all three of them, are either irrational or imaginary, right? But if it does exist, if there is a rational zero, it is one of these ones. It has to be one of these ones. Alright, let's move on to 32. Make a list of the possible roots using the rational roots theorem. Write each function in factored form. Alright, so it's a perfect example. We're not going to factor by grouping. It actually doesn't work. So we're going to take the 60, right, the constant, find all of its factors, which are, there's a lot of them, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 12, plus or minus 20, plus or minus 30, jeez, and finally plus or minus 60. I hope we don't have to test all of those, but there is a lot. Let's start testing though. The sooner we get started, the faster we're going to get through it. 1, 2, negative 23, and negative 60, right? That's what you're going to do. You're going to put all those numbers and get ready for synthetic substitution, synthetic division. I'm going to start with 1 because I always hope that that is one of the zeros. It's is the easiest one to test. Bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 23 plus 3 is negative 20. 1 times negative 20 is negative 20. That gives you negative 80, so no, not 1. Alright, how about negative 1? Alright, so let's start again. Bring down the 1. Negative 1 times 1 is negative 1. 2 minus 1 is 1. Negative 1 times 1 is negative 1. That's negative 24. Negative 1 times negative 24 is positive 24. Nope, doesn't work. Alright. We're moving swiftly. We tested 2 already, so let's test out 2. Did I mess up? Yes, I did. Here. 2. Alright. So bring down the 1. 2 times 1 is 2. That's 4. 2 times 4 is 8. Negative 23 and 8 is negative 15. 2 times negative 15 is negative 30. Nope, doesn't work, right? Because negative 60 and negative 30 give you negative 90. Let's test out negative 2. Bring down the 1. Negative 2 times 1 is negative 2. That's 0. Negative 2 times 0 is 0. That's negative 23. Negative 2 times negative 23 is positive 46. No, it doesn't work either. Jeez. Okay, let's keep going. It's alright. Let's not give up. Let's keep trying. Let us try 3. So then you're done there. But if they did want the zeros, you would write them like this, right? They don't want them. They just want it in factored form. So you're done at that point. All right, let's do 34. 6x cubed minus 7x squared minus 9x minus 2. Same thing. What you do is you start with the constant, negative 2. And you list all of its factors. Pretty easy. It's just plus or minus 1 and plus or minus 2. Then you take the leading coefficient, which is 6. And you list all of its factors. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then you come up with all the different combinations where this one over this one, right? It's always the factors of this one over the factors of this one. So what are the possible numbers we're going to test? To test, possible values are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 1 over 6, and plus or minus 2 over 6, right? Make all the different combinations you can where these are the numerators and these are the denominators. Now we can eliminate some of these because they're actually the exact same thing, so let's do that. Plus or minus 1 over 1 is just plus or minus 1, right? Plus or minus 2 over 1 is just plus or minus 2. plus or minus 1/2 is unique. Plus or minus 2 over 2, we can cancel it because that's just 1. Plus or minus 1 over 3, that's unique. Plus or minus 2 over 3, that is unique. It's not repeated anywhere else. Plus or minus 1 over 6, that's unique. And plus or minus 2 over 6, we can cancel that one because that's 1/3. And we already have 1/3 right here. Alright, so there actually does not that many to test out, although we do have some fractions we're going to have to be dealing with. Let's hope that it's either 1 or 2 or -1 or -2, right? But if it's not, we have to test those fractions. Alright, let's set it up for synthetic division. 6, -7. Are there any missing ones? No, no zeros here, right? Just -9 and -2. Alright, let's start with 1. That's going to be our first number. Here we go. Starting with 1. Bring down the 6. 1 times 6 is 6. That's -1. That's -1. That's -10. That's -10. That's -12. So no. Didn't work. Alright. Let's move on to -1. Bring down the 6. -1 times 6 is -6. That's -13. That's +13. That is 4. That's -4. And that's -6. So no, again, it doesn't work. Alright, how about 2? Let's try 2. Bring down the 6. 2 times 6 is 12. It's -7 plus 12 is 5. 2 times 5 is 10. 10 minus 9 is 1. 2 times 1 is 2. There it is. We found it. Alright. Good. We found x equals 2. That's the first one. What we're going to do again is take our leftovers, 6, 5, and 1, turn it into a polynomial, 6x squared plus 5x plus 1. And we're going to try to do x factor. If it doesn't work, we have to go with the quadratic formula, okay? So just get used to that idea that if x factor doesn't work, you have to go with quadratic formula. 6 times 1 is 6, b is 5. Two numbers that multiply to make 6 but add up to make 5. Oh yeah, it does work. It's 2 and 3. There you go. So we're going to set this up. It's going to be 6x squared plus 2x plus 3x, right? Those two come from here, plus 1. And then factor by grouping. It should work. It has to work. If you do x factor and you did your numbers correctly, factoring by grouping should work here. We're going to divide by 2x on this one. And on the other one by nothing, by 1. So we're going to factor out 2x from the first one. We're going to get 3x plus 1. For the other one, we're going to factor out a 1. And we're going to get 3x plus 1. And there it is. It's 3x plus 1. And 2x plus 1. And the other one that we had already found, which is x equals 5, that one gives us x minus 5, right? The factor that gives us that 0 is x minus 5, so let's not forget that one. Put that one here, and now we're done. What is this one called? H of x. So we're going to write h of x equals, and that is our factored form. Okay, the next one we're going to do is number 35. It says solve the polynomial equation by finding all the roots. So just like the ones above, they don't want us to just factor, they actually want us to find all the roots, which is basically the same process, right? So find all the roots. Let's start by, does factoring by grouping here work? No, it doesn't seem like it, right? If I try to group these two together, the only thing I could factor out is x squared. If I try to group these two together, I could factor out a 2, but it's not going to help me. They're not going to be the same. So basically, we're going to do the same thing we did in the last one. Start with the 4. List all of its possible factors. Then the 3, right, the leading coefficient. List all of its possible factors. And then the possible numbers, the possible rational roots are, let's make combinations now. Plus or minus 1 over 1. Plus or minus 2 over 1. Plus or minus 4 over 1. Plus or minus 1 over 3. plus or minus 2 over 3, and plus or minus 4 over 3. It looks like they're all unique. None of them repeat, right? They're all different. The only thing I'm going to do is just clean up those that have 1 over 1 because they're pretty easy. They're just 1s, 2s, and 4s, right? So this one's just going to be plus or minus 1, plus or minus 2, plus or minus 4. And then those other ones on top. So we're going to test those and those. These are the same as these. I just decided to take out the ones. Alright, we're going to test them out with synthetic division using 3, negative 10, positive 10, and negative 4. And let's start with 1. I always hope that 1 is the factor. It's the easiest one to test out. Let's bring down the 3. 1 times 3 is 3. Negative 10 minus plus 3 is negative 7. That's negative 7. That's 3. That is 1 times 3, which is 3. And that's negative 1. Almost 0, but not quite. So no. Let us try negative 1. Bring down the 3. Negative 1 times 3 is negative 3. That's negative 13. Negative 1 times negative 13 is positive 13. That's 23. Negative 1 times 23 is negative 23. Nope, doesn't work either. Alright, move on to 2. Bring down the 3. 2 times 3 is 6. That's negative 4. 2 times negative 4 is negative 8. That is 2. 2 times 2 is 4. Yes, we found it. It's x equals 2. That's the first one. Now we're going to take the remaining coefficients, turn it into a polynomial, right? Minus 4x plus 2. And we're going to try to solve that. Let's try x factor. It's been working in the last couple of examples. So that's 3 times 2, which is 6, and negative 4. It seems like it stopped working because I don't see anything. Two numbers that multiply to make 6 and add up to make negative 4. Negative 3 and negative 2, nope. Negative 6 and negative 1, nope. Positive 6, positive 1, no. Nope, nothing works. Alright, you know what that means. We're going to take this and plug it into the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Alright, plug in those values. X equals negative b, that's negative 4, because b is negative 4, right? So negative 4, that means 4. Plus or minus the square root, b squared, that's negative 4 squared, that's 16. Minus 4 times a, which is 3, times c, which is 2. All over 2 times a, which is 3. Alright, we're going to continue this up here. So it's x equals 4 plus or minus the square root of 16 minus 4 times 3 is 12 times 2 is 24. All over 6, 2 times 3. So keep going, 4 plus or minus the square root of, let's zoom in a little more, negative 8, right? Positive 16 minus 24 is negative 8, all over 6. Alright, I'm going to keep going with that negative, because as soon as you guys see a negative inside, you take it out and you turn it into I, all over 6. And just like in the last one where we had a radical, we are going to simplify it now. So let's take that 8 and break it down. Radical 8 is 2 times 4. 2 is done. 4 is 2 times 2. So what you have is 3 2's. So it's radical 2 times 2 times 2. Let's break them out of jail. Pairs. Here's a pair of 2's. One breaks out, the other one dies. The other 2 here stays in there by itself. So 1 2 comes out and a 2 stays inside. 2 radical 2. Alright. So using that, I'm going to replace that radical 8 with 2 radical 2. Here's what you have. 4 plus or minus. The 2 comes outside, right? This is what I have. I, and then the radical 8 is 2 radical 2. All over 6. Now this just looks weird, the I before the 2, so I'm going to just flip them around. It's the same thing, so it's 2i. 4 plus or minus 2i radical 2 all over 6. And now the last thing to do is notice that the numbers that are outside, only the numbers that are outside, all have something in common. You can divide them all by 2. So let's do that. You divide them all by 2 and you get 2 plus or minus 1i, which is just I, radical 2 all over 3. Now we don't like to leave them like this with the plus or minus anymore. We like to actually separate them from one from each other because we need 3 roots. We already found one, right? Let's see where we find it. Right here. X equals 2. The other 2 are right here, which are 2 plus I radical 2 over 3 and 2 minus I radical 2 over 3. And the 2 that we had found earlier. Those are all the roots, all the zeros. Let's continue with 38. X to the 4th minus 5x cubed plus 3x squared plus x equals 0. Before you go and make a mistake here, notice that they all have x. So factor it out. That is a GCF. They have a GCF. That's different from like the one we just did. Look at that one. That one doesn't have an x, so we didn't have a GCF to factor out. That not all of them don't have something in common. And this one they do. All of them have x, so factor it out. What you're gonna have is an x outside. No, I don't like red right now. What you're gonna have is an x outside, and then inside you're gonna have x to the 3rd minus 5x squared plus 3x plus 1 equals 0. And then you're going to try to factor this by grouping, but nothing works, right? These two, the only thing they have in common is x squared. These two, the only thing they have in common is 1, so it doesn't work, which means that you're going to have to do synthetic division for this one. Using this, so that means that you only have 2 things to test, right? The constant is 1. So what are the factors of 1? Plus or minus 1. That's it. The coefficient is 1, so 1 over 1, which is just 1. So something is going to work really quick. 1, negative 5, 3, and 1. And we're going to try 1. Let's see. Bring down the 1. 1 times 1 is 1. Negative 5 plus 1 is negative 4. That's negative 4. 3 minus 4 is negative 1. Negative 1 times 1 is negative 1. And that's 0. There we go. It is 1. So x equals 1 is the first one. That is your first root, your first 0. We're going to take the remaining coefficients, turn it into a polynomial, x squared minus 4x minus 1, and we're going to solve that. You are not going to make it work with x factor, right? That's impossible. Think it's 1 times 1, 2 numbers that multiply to make 1 and add up to make negative 4. Doesn't work. So we're going to plug them into the quadratic formula again. Oh, by the way, we already have 2 zeros, I forgot. We have x equals 1, which came from here. We also have this one. X by itself, when you factor out, as soon as you factor out, that already gave you a 0. You set that equal to 0, and that is your other 0. X equals 0 is another one. So there you go. We have 2. We need 4, right? X to the 4th. That means that we need 4. We need 2 more, and they're going to come from here. We're going to use the quadratic formula to solve that. So it's going to be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's plug them in. B is negative 4. Negative 4. A is 1. C is negative 1. A is 1. Simplify that. Erase all this junk over here from an earlier problem. So it's going to be x equals negative negative 4, that's 4, plus or minus the square root of 16. Look at this one. Negative times positive times negative. That's going to be positive 4 plus 4 all over 2. So x equals 4 plus or minus radical 20 all over 2. We are going to simplify the radical 20. Here we go. Factor 3, that's 2 times 10. That's 2 times 5. So it's a 2 a 2, and a 5. 2, 2, 5. We're going to put the two 2's together, bring one out, the other one dies. The 5, it stays by itself inside. So 2 radical 5. So I'm going to replace the radical 20 with that 2 radical 5. So this is what I have. X equals 4 plus or minus 2 radical 5 all over 2. And again, notice that the numbers that are outside all have something in common. So if they do, then you go ahead and simplify it. They can all be divided by 2. So it's x equals 2 plus or minus radical 5 all over 1, which I don't need to write it because it's just 1. So those are the other two zeros. I'm going to write them over here next to the other ones that I already wrote, but separate. X equals 2 plus radical 5, and x equals 2 minus radical 5. Remember, the plus or minus means that there are two solutions there, a plus and a minus. There you go. We found all 4 of them. Okay, we're going to finish this video, part 2, with number 39, the last one. Hopefully you guys were able to easily find the error. It says 2 students use synthetic division to divide 3x cubed minus 2x minus 8 by x minus 2. Determine which solution is correct. Find the error in the other solution. So if you analyze them carefully, you'll notice that the student A used 3, 0, negative 2, and negative 8. First question you should have is where that 0 come from. And you should notice that it's missing the x squared. So 3x cubed plus 0x squared minus 2x minus 8. The numbers look correct there. Also, since you're dividing by x minus 2, then the number that goes here in the box is positive 2, right? Because x minus 2 is a factor, but what is the 0 that you're testing? It's 2, right? This factor gives you a 0 of 2. You bring down the 3 and it's 3. 2 times 3 is 6. That's 6. 2 times 6 is 12. That's 10. 2 times 10 is 20. And that's 12. So everything seems correct. In student B, he set it up correctly, 3, 0, negative 2, and negative 8. The work seems correct, right? Negative 2 times 3 is negative 6. 0 minus 6 is negative 6. That's positive 12. That is 10. That is negative 20. That's negative 28. The mistake is here, right? You should have noticed that right away. When you're dividing by x minus 2, when you're trying to do this division, this is the factor. The number you're actually going to use is positive 2, not negative 2. This division is correct if he was dividing by x plus 2. But he's not. He's supposed to be dividing by x minus 2. So student A is correct. Correct. And what's wrong with student B? That's incorrect. Alright, this concludes part 2 of the video. Go back and rewatch every little problem that you did not understand that well. You know that the test is tomorrow and you're running out of time. I know that it's kind of late posting this video right now, but try, practice. Maybe you might want to just wake up early and watch it again a couple of times before the test, okay? Only those examples that you need, of course. You don't have to watch the full 2 hours of the video that I have. Alright, good luck.